Hello, my name is Oliver Mays, and I head the Research and Development Department here at ECOROLL AG. Today I'd like to give you a brief insight into our research activities and present a research project that we completed this year, which we carried out together with the Institute of Manufacturing Technology and Machine Tools in Hannover. And it's basically about significantly improving the deep rolling process by wanting to control it. And not just controlling the rolling force as a parameter, that seems relatively simple and obvious. No, we wanted to control the surface pressure between the tool and the component in order to significantly reduce the difference in residual stress between different components. This is crucial when I have components that are designed to be particularly safety relevant, and we really can't afford to make any mistakes in the process design. Deep rolling itself is a process that strengthens and changes a component through mechanical stress. A rolling roller or a rolling element is pressed onto the surface of a component by mechanical force, rolls off there, and creates a plastic deformation of the surface. In the process, the surface is smoothed and compressive residual stresses are introduced and work hardening occurs, so that the hardness in the near surface area increases. The result of this is that we have a significantly increased service life. So we have cracks that are initiated later under dynamic load. We have cracks that grow more slowly. We have an overall increased strength. We have a counterplay, so to speak, between load stresses and residual stresses. So if we have tensile stresses, tensile load stresses, then the compressive residual stresses basically counteract them, right? And reduce the resulting load, right? That's all very positive, and thus the service life of a component can really be increased very significantly. This is also frequently used, but especially with components where service life is critical, we have a major disadvantage with deep rolling. Quality assurance is a bit more difficult. Deep rolling is a very reproducible and very good process. The problem is, once I've carried out the rolling process, applied rolling forces, contact pressures, monitored my roller geometry, everything, then I can be relatively sure what near surface area properties will result. And I can also measure these somehow in the end. Measuring is just, especially with the near surface area properties. So with residual stress and hardness, the whole thing becomes relatively difficult. Right? Residual stress and hardness are, in this case, values that I can only measure destructively, so I can't use my component afterwards. That is, of course, when I'm manufacturing a safety-relevant component, relatively unpleasant, because I actually have to check every component I produce. And of course, in the end, well, I want to use it. That's why we introduced our EcoSense technology a long time ago, to at least monitor this process, so that you can really monitor every single component that is manufactured and say that the component was deep rolled with the correct process parameters. And thus, at least on the part of the deep rolling process, no error occurred. What we cannot measure in this process, however, is whether there are any deviations beforehand. Because for the residual stress and also for the strain hardening, the rolling force is not actually the decisive factor, but it was basically also pushed relatively strongly by the University of Bremen by the Leibniz IWT. The so-called process signatures. Process signatures are internal load states within the near surface area that ensure that a specific near surface area state is created. So in deep rolling, for example, it could be the surface pressure, right? The surface pressure determines how strongly my residual stresses develop, right? That's a connection that's still being investigated a bit scientifically, but generally speaking, the rolling force is not the decisive factor, but the interplay between force and contact geometry is crucial for how much compressive residual stress is created and how much strain hardening occurs. And that's exactly what we wanted to find out in this process or in this project. Can we regulate that somehow? We've expanded our EcoSense technology a bit more for this, upgraded it so that it can communicate with the machine, so that we can, for one thing, specify forces. Locally resolved, so depending on the position in my NC code, we can specify a process force. And this process force is then also regulated via a feedback loop, a control system via the feed of my tool, regulated again. We first set up this control loop. That was also relatively easy to do, to regulate the rolling force in a locally resolved manner. Now the second part is added, that we want to regulate the contact pressure. And now we can design the process so that at every point we have a different force, but always a constant, for example, Hertzian pressure. What we still don't know is how our pre-process influence our actual component. Now we can design this for our ideal component, What we don't know is, do we perhaps have, due to wear in my turning tool, any changes in the geometry? Is my radius that I'm moving through maybe not 3.3, but maybe only 3.28 or something like that? That could already change the residual stress state, and that's exactly what we used our EcoSense for. We actually used the EcoSense and its force measurement to calculate back what geometry my component had at that moment. And with that, we can then start again at the beginning for the next component in the next step, recalculate the force profile, and add it again as new set points. I'd like to show that the whole thing also had an effect on the residual stress using this example. We carried out tests in the project here in which we took a component which now had a, let's say, freely invented shape here with various design elements, and we determined the residual stress at 6 different points on this component after we manufactured it. And we have deep rolled this component with various process forces, so to speak. In the first variant, we simply specified a constant rolling force of 700 newtons for the entire machining path. And then we determined the residual stress at the various points, so to speak. And we get different residual stresses depending on the point and the contact pressure, as it were. And that's shown here in the diagram on the left side. It's the residual stress difference between the maximum and minimum residual stress values. And then we rolled the same component again, well, not the same one, but the same geometry to be scientifically accurate, and designed this component, or the rolling process, in such a way that the Hertzian pressure has the same value at every single point of this component. Even there, we didn't check if that's the most optimal Hertzian pressure or anything, but rather we settled on one value and processed it based on that. And you can already see in the diagram below that the rolling force is sometimes higher or lower depending on the geometry. Based on that, we can already say that I need more or less force at one point to generate the same pressure. We added that again as a target profile and carried out the process. The corresponding process forces are also plotted below. And you can see that we were able to follow this target line very well. And then we determined the residual stress at these 6 points again. And what we see is that the variance of the residual stress, the difference between the highest and lowest values, is reduced by up to 50%. That means we're coming much, much closer together. Of course, we don't have residual stress, let's say equality or constancy yet, right? So the residual stresses still vary throughout the process. But we've already reduced the difference by 50%, which is a very, very strong value. And now we can also regulate the whole thing accordingly. And once I've processed the whole thing for a component, I measure the geometry. If I get a change in my geometry over time, I can determine this force profile anew for each component and then process each one identically. And to show that this control works, I've brought along another short video for you. In the left part, you see a component, basically the same component that was deep rolled in the same way with the same process parameters and target force curves. But once with the control switched on and once with it switched off. On the left without control, on the right with control. And if you follow the graph below, the dashed line basically corresponds to the target specification for how high the force should be. And in blue, so to speak, the corresponding real rolling force as it currently is in the process moves along with it. You can see that without control, we deviate significantly from the process. That might be because the tool isn't ideally calibrated or something, right? But you can see that we're generally further away. And that we especially also have a deformation, an elastic deformation of the component due to its long overhang, which causes the rolling force to vary accordingly. And the closer I get to the clamping, the higher the rolling force becomes, so to speak, if my component, or rather my tool, only performs a linear movement, for example. I can see that first of all, on the right side then, the whole thing with the control switched on. We didn't recalibrate the tool or anything here, but simply started the same process once again. And you can see that we really follow this target line very, very well. There are always individual jumps where it might not work quite so well yet. We might have to adjust the control parameters a little bit more there, but overall, this is a very, 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 very good result for such a research project. And we are very happy and grateful that we were able to carry out this project in this way. And we hope to be able to build a corresponding product from this in the near future, which we can then also bring to the market and offer to you accordingly. With that, I would like to thank you very much for your attention. If you have any questions about this, about the general research project, or about our work in general, please do not hesitate to contact me or my colleagues at ECOROLL AG. And at this point, also a big thank you to the Institute of Manufacturing Technology and the ZIM, who funded this project